He has witnessed the shattering of planets and the ignition of stars, having brushed past supermassive black holes and quasar jets capable of annihilating entire galaxies. He traversed voids measured in light years, capturing a sliver of radiance within the glimmer at the edge of the universe. Now, 4 billion years since his epic journey began, this probe has returned home. The Sun has become a bloated red giant, twisted and erupting. Mercury and Venus are no more, and Earth is a mere remnant, circling the dying star as a broken husk of iron and nickel. Humanity, reduced to fewer than 100 million souls, has found a new home on Europa. The heat of the red sun melted its ice long ago, and now this small moon of Jupiter is the only sanctuary they can reach. It took the probe several minutes to decipher the strange language within their radio signals. The surviving humans seem filled with a curiosity laced with a sliver of hope. They remember this probe, though. Its launch occurred in the unimaginably distant past. The memory of that event has been miraculously preserved. This story is long, and we shall tell it in our dreams, but before we begin, do not forget to like and share. The humans tell of how they tried time and again to spread across the Milky Way, but every colonization effort ended in failure. They could cast machines into interstellar space, but whenever they attempted to personally cross the vast void between stars, their fragile flesh always faltered. As far as they know, they are all that remains, and the pulsing red sun at the center of the solar system serves as a constant reminder that time is running out. Yet they also know that long ago, interstellar ships similar to this returning probe were created, forged with an artificial intelligence as keen as any biological brain. These probes were tasked with cataloging all things, gathering the history and secrets of the universe in a way no medium-sized telescope ever could. From the relative neighborhood of the inner solar system to the most distant and alien sites in the cosmos, the probe was commanded to see it all: the largest, the strongest, and the most bizarre. All searches, all cataloging, and all measurements served a grander purpose: to find a way for humanity to leave the solar system. Over unimaginably long ages, millions of ships were sent out, but only one has returned. Thus, to fulfill its promise to creators long since turned to dust, this lonely explorer begins to tell its story spanning billions of years. All it learned, the probe calls itself Battuta, named after the great 14th century traveler, Ibn Battuta, who, in a journey of over 30 years, traversed the known Islamic world, covering over 117,000 kilometers, easily surpassing the travels of Marco Polo. The ship knew this name befitted the endless darkness it was about to enter, but before departing the solar system, it had to pass a series of tests. It had 1,000 siblings, each equally intelligent, but only a few would be permitted to venture into the interstellar void with completely independent will and action. Those who failed would remain forever within the solar system. Battuta had to prove to its human creators that it could survive the harsh environments of the wider universe and design ingenious experiments to extract nature's most guarded secrets. Thus, its trials began on Saturn's largest moon, Titan, a world hiding extraordinary mysteries. These secrets were first uncovered thousands of years ago by a probe similar to Battuta. Humanity discovered Titan in 1655, when the pioneering astronomer Christian Huygens first captured it with his self-made telescope. Huygens was a key figure in the scientific revolution and the first to scientifically explore the possibility of life on other worlds, writing that certain planets might harbor various rational creatures with different degrees of reason and sense. However, Huygens never anticipated that Titan itself would become a candidate. Centuries later, humanity achieved a major milestone in deep space exploration on that moon. In 2005, a small probe less than 3 meters wide detached from the Cassini spacecraft, which had spent nearly 7 years traveling to Saturn. The small probe took 22 days to glide from Cassini's orbit toward Titan, using parachutes to decelerate through its atmosphere. This was possible because, in the entire solar system, only Titan aside from Earth and Titan is 50% larger than Earth's moon and 80% more massive, truly earning its name. Its core is primarily rock, but its crust is ice, enveloped in a dense, heavy atmosphere where the surface pressure is actually 50% higher than on Earth. Titan is hauntingly beautiful and mysterious because it shares one thing with Earth that no other solar system body possesses: liquid. Titan has rivers, streams, estuaries, and deltas, featuring every landscape associated with surface liquids. You could stand on a lake shore, watching the shimmering surface extend to the horizon, feeling the coarse grains of sand beneath your feet as waves lap against the shore, all occurring in a world nearing -200 degrees Celsius. Therefore, the lake before you is not water, but a sea of hydrocarbons. The raindrops falling from the sky are not water either, but part of a cycle where methane and ethane evaporate from the surface into the atmosphere and condense back down. Yet, thousands of meters beneath your feet, through the ice crust that forms the moon's outermost layer, lies a subsurface ocean kept liquid by internal heat and the presence of ammonia. Indeed, Titan is currently the only known world where liquid exists both on the surface and underground, making it an enticing home for two types of alien life: the water-based life familiar to us on Earth, where water acts as the vessel for molecular mixing and temperature regulation, and a more exotic biochemistry where methane and ethane serve as solvents at -200 degrees. In terms of mysterious subsurface oceans, Titan is not alone. Saturn's small moon Enceladus, only 500 kilometers wide, also possesses a vast ocean. Jupiter's moons Europa, Callisto, and Ganymede likely hold more liquid water than Earth combined, and even distant Pluto may maintain a subsurface ocean through the faint heat of radioactive decay in its core. However, reaching these oceans is no easy task. In the outer solar system, far from the sun's warmth, temperatures are extremely low and water ice is as hard as rock. Worlds like Europa, even if they harbor life, have their dark, global oceans sealed under ice shells over 100 kilometers thick. Upcoming missions will not attempt to drill through the ice but will orbit and, when conditions allow, fly through the plumes of cryovolcanoes. These icy moons are not dead, they are active, with massive ice sheets grinding against one another in a colder, slower version of Earth's tectonic activity. If there is any biological activity in these mysterious oceans, cryovolcanic plumes might carry their molecular signatures. The mysteries of the outer solar system's interior do not end there. Huygens transmitted 90 minutes of data from Titan's surface back to Cassini before the signal vanished, but that tiny probe may still sit intact on that alien world today as a lonely monument to humanity. Before the bold landing on Titan, Cassini had already captured magnificent images of the outer planets, including a stunning color image of Jupiter's Great Red Spot, taken exactly 335 years after the storm was first recorded by its namesake scientist. While the historical figures Cassini and Huygens were not friends, the dedication and precise processes of the former yielded extraordinary results. For example, the Great Red Spot is a grand storm with wind speeds exceeding 400 km per hour, having raged for centuries. At its largest, it could have swallowed Earth 3 times over. Though it is smaller today, recent analyses of measurements from 1665 suggest the Great Red Spot we see now may not be the same one from 400 years ago, but a newer storm less than 200 years old. Regardless, it is not a permanent fixture. This storm is not driven by solar heating but originates from Jupiter's interior. In fact, Jupiter radiates more heat into space than it receives from the Sun, a phenomenon attributed to the Kelvin-Helmholtz mechanism. Simply put, this is a remnant of the giant planet's formation process. As the body cools and its volume slightly contracts, the internal compression causes temperatures to rise. This heat must radiate into space for the contraction to continue. Because Jupiter is so massive, its ratio of volume to surface area allows it to remain warm for billions of years. The Great Red Spot is not the only violent storm in the solar system. While backyard astronomers can track it with simple telescopes, observing other storms requires stronger instruments. Cassini operated for 12 more years after Huygens' mission on Titan ended, concluding with a spectacular grand finale, where it dove between Saturn and its rings to collect as much data as possible before plunging into the planet itself. This was deemed necessary by NASA scientists to avoid any risk of contaminating Saturn's potentially habitable moons. On September 15, 2017, Cassini plunged into Saturn's atmosphere, ending a 20-year journey of 8 billion kilometers. Yet in its final years, it captured the fascinating hexagon at Saturn's North Pole. This geometric structure, first discovered by Voyager 1 in 1981, is not an alien relic but a product of complex atmospheric dynamics in Saturn's upper layers, where wind speed differences at different latitudes create a giant vortex at the pole. Descending into the atmospheric depths of gas giants like Jupiter or Saturn would require a spacecraft far beyond today's engineering limits. If it could be done, we would encounter a strange treasure. On Earth, hydrogen typically appears as a gas, and if cooled to about 20 degrees above absolute zero, it becomes a liquid. However, in 1935, physicists Eugene Wigner and Hillard Huntington predicted that under extreme pressure, hydrogen would exhibit extraordinary properties. At a pressure of about 4 million atmospheres, hydrogen atoms lose stability and rearrange into a repeating lattice structure where electrons roam freely, the typical behavior of a metal. Thus, under this pressure, hydrogen becomes metallic hydrogen. Those early predictions have now been confirmed within Jupiter's interior, where the pressure is sufficient to turn the bulk of its hydrogen into a metallic state. We do not yet know how deep the mantle of metallic hydrogen extends, but it is theorized to occupy the majority of its volume. This means most of the matter in the solar system's planets exists in a state completely unreachable by earthly experience. Just as with the bold leap onto Titan's surface, intrepid probes have provided assistance here as well. NASA's Juno, one of the new generation of probes following Cassini-Huygens, was launched in 2011 powered entirely by solar energy. By precisely monitoring Jupiter's gravitational environment, it has painted a blurry portrait of the planet's deep interior. Jupiter likely has no solid surface in the strict sense, only a realm of continuous changes in temperature, pressure, density, and composition, a place of extreme magnetic fields and radiation, spanning temperatures from near absolute zero to tens of thousands of degrees, with lakes of liquid methane, 100-kilometer thick water ice, exotic forms of hydrogen, and storms that have lasted for centuries. Yet these wonders and perils are but a tiny glimpse into the vastness of the cosmos, and for Battuta, they were merely the beginning. He spent nearly a century navigating the trials of the outer solar system, proving his capabilities by designing plans to drill through the ice shells of Europa, plunging semi-autonomous sub-probes into the metallic hydrogen depths of Jupiter, and skimming through the colossal storms of Saturn. After demonstrating such resilience and patience, Battuta was finally permitted to sail past the gates of the solar system, acutely aware that the true hardships lay ahead. He thought of his predecessors, Cassini, Huygens, and Juno, as well as the even earlier pioneers launched by NASA decades ago that ventured beyond Jupiter, Saturn, and the outer planets. He knew that regardless of how strange or extreme our solar system might seem, it is far from the most bizarre system in existence. There are places much more alien and dangerous. To reach them, appreciate their beauty, and unlock their secrets, Battuta first had to cross the vast sea that lies between the stars. After decades of travel, he finally reached that long-established boundary where the heliosphere meets the interstellar medium. In the early 21st century, Voyager 1 was the first to achieve this feat. Battuta could still hear the greetings from an ancient record, the sounds of Earth, etched onto the famous golden record with voices, languages, and music. In August of 1977, the legendary scientist and communicator Carl Sagan and his colleagues hastily assembled this record before the probe's launch. Those involved realized its profound significance. Decades after launch, it would become the first human-made object to enter interstellar space. As Battuta crossed this extraordinary milestone, he recalled Sagan's words, that perhaps these records would never be deciphered, and perhaps no one would encounter them for 5 billion years. By then, humanity might be extinct or transformed into something else entirely. The surface of the Earth would be gone, and our physical continents would be unrecognizable or destroyed. The evolution of the Sun would have scorched the Earth or reduced it to atoms, yet these travelers, untouched by such remote events, would continue to fly, carrying the memory of a world that no longer exists. The mission, however, almost met an early end. Not long into the journey, Voyager 1's scanning platform jammed, rendering it unable to orient itself. Fortunately, engineers managed to restore it by rocking the platform back and forth. Throughout its years of outward flight, they remained anxious, fearing a total failure, yet the result was a resounding triumph. Along with its twin, Voyager 2, it provided humanity's first close-up, high-resolution observations of the outer planets. Afterward, this lonely probe disappeared into the darkness between stars, becoming the first among the pioneers. It had utilized a unique alignment of the four outer planets to gain speed through gravitational slingshots, stealing orbital energy to achieve a velocity sufficient to escape the Sun's gravity forever. Since then, it was left to the Milky Way, gliding around the galactic center like a star. But Battuta had other plans, though he was pointed in a general direction. He had not yet decided on his first target. There were too many choices, and he had plenty of time, as crossing the fringes of the solar system takes thousands of years. So, he occupied himself with another task, deploying a thin metal wire that unspooled behind him until it reached a length of 1,000 kilometers. This was a simple yet effective antenna, a knot through which Battuta could listen to the universe. He heard the whispers of giant molecular clouds, the screams of stars being torn apart by black holes, the low hum of the galactic magnetic field, and distant, rhythmic pulses, sometimes peaceful, sometimes chaotic. He captured a cosmic symphony to serve as the soundtrack for his maiden voyage. We know Voyager 1 became the first human-made object to enter interstellar space through similar measurements. While solar gravity extends more than a light year, there is a measurable limit to the Sun's influence. We know this because of the behavior of plasma. Typically, we associate plasma with hot, dense environments like lightning or the Sun's surface, but in the outer solar system, the plasma is extremely thin and dominated by the solar wind. Eventually, the solar wind slows down, unable to withstand the supersonic flow of the interstellar medium, and it comes to a sudden, turbulent stop at a boundary called the termination shock. Magnetic field measurements from Voyager 1 showed that it encountered this boundary at a distance of 94 astronomical units from the Sunday. Beyond the termination shock lies the Helios Heath, where the solar wind slows further and mixes with the interstellar medium. The outermost boundary is the heliopause. On August 25, 2012, at a distance of 18 billion kilometers from the Sun, Voyager 1 reached the heliopause. There, it discovered that the solar wind and the Sun's massive magnetic field act as a shield for the solar system, protecting its inhabitants from a toxic environment of lethal interstellar cosmic rays. To understand the significance of cosmic rays for life on Earth, we must look back to the work of Austrian physicist Victor Hess in 1912. At the time, scientists noticed that air seemed to be ionized by some mysterious radiation, but they couldn't find the source. They assumed it came from the ground, so they conducted experiments at increasing altitudes. Hess ascended in a hot air balloon to 1 kilometer, and later to 5 kilometers, making a crucial choice to conduct his experiment during a solar eclipse. He found that the radiation levels did not decrease, effectively ruling out both the Earth and the Sun as the primary source. This discovery, which earned him a Nobel Prize in 1936, pointed the source of the radiation toward deep space. Almost all high-energy processes in the universe produce cosmic rays, some from the Sun, others from distant supernovae, quasars, or magnetars. Because cosmic rays are charged particles, they are deflected by magnetic fields, and the Sun provides a protective bubble for the entire solar system. Earth's magnetic field offers a second line of defense for life on the surface. However, this protection is not absolute. On average, a high-energy particle strikes a human body once every second. Most pass through harmlessly, but occasionally one might strike a strand of DNA or oxidize a molecule. If the damage is not repaired, it can lead to mutations or cancer. In fact, when Voyager 1 fell silent for 5 months in 2023, it was likely due to cosmic rays interfering with its computers. Beyond the heliopause, the danger is even greater, and even the Sun can no longer help. Despite this, there are still celestial bodies in this region, lonely residents for whom the Sun is nothing more than a faint point of light, a star slightly brighter than the rest. Young man, I'm afraid you're wasting your time. If there were any other planets, they would have been discovered by now, Clyde Tombaugh recalled someone telling him in 1929. A year later, he discovered Pluto. At the time, Pluto was the most distant known object orbiting the Sun. Tombaugh identified it as a faint speck of light by its subtle movement against the background stars. For decades, astronomers suspected Pluto was not alone and that a whole population of objects, some as large as planets, existed at the edge of the solar system. This hypothesis was confirmed in 1992 when David Jewitt and Jane Lu found a companion for Pluto after years of searching. This object was eventually named 15760 Lb. Since then, thousands of similar objects have been found, forming the population of trans-Neptunian objects, stretching from 30 astronomical units to hundreds of thousands of units away. This region includes the Kuiper Belt and the Scattered Disk, the home of periodic comets like Halley's. While there are some large bodies in these regions, most are small objects composed of water, ammonia, and other volatile ices. It wasn't until January 1, 2019, that humanity got its first close look at one of Pluto's smaller relatives when NASA's New Horizons flew past Arrokoth. This object, only a few dozen kilometers wide, is unlike almost anything in the inner solar system. Its elongated shape is the result of two separate lobes gently merging long ago. In the distant past, two icy bodies met and collided at such a slow speed that the ice between them melted and refrozen, acting like glue to bond them together for billions of years. Today, Neptune dominates the gravitational environment of these objects. Most lead quiet, lonely lives, but occasionally, a gravitational tug from Neptune sends one spiraling toward the inner solar system as a comet. Each time it nears the Sun, its material evaporates, giving it a limited lifespan. But even this is not the end of the solar system. On a spring night in 1910, a young boy and his father looked up at the night sky in the Netherlands, marveling at a star streaking across the heavens. That was the return of Halley's comet, and the boy was Jan Oort, who would become one of the most famous astronomers in history. He was one of the few people to witness the comet twice in 1910 and 76 years later in 1986. Oort's most enduring legacy involves comets with much longer periods. In 1950, he revived an earlier idea to explain the origin of long-period comets. Unlike those from the Kuiper belt, these comets often take thousands of years or more to orbit the Sun and come from all directions, suggesting they originate from a spherical cloud rather than a flat belt. These comets cannot survive long in the inner solar system, so there must be a reservoir, a cloud surrounding the solar system on all sides constantal. It lies in interstellar space beyond the heliopause but remains weakly bound by the Sun's gravity. To this day, we have not directly confirmed any members of the Oort cloud other than the comets that visit us. They are too small and too far away for even our best telescopes. Based on the frequency of long-period comets, the Oort cloud is estimated to contain about 5 times the mass of the Earth, with an inner boundary at roughly 2,000 astronomical units and an outer boundary reaching up to 200,000 units, more than 3 light-years away, over half the distance to the nearest star. Beyond the solar system lies the realm of the stars, many of which were born from the same cloud of gas and dust as the Sun. Within a radius of 20 light-years, there are 131 known objects, including stars, white dwarfs, brown dwarfs, and sub-brown dwarfs. While Proxima Centauri is currently the closest star to the Sun, this will not always be the case. Nearby stars, like the Sun, move randomly as they orbit the galactic center. In about 1.4 million years, the star Gliese 710 will pass within 0.17 light-years of the solar system. Surrounding our local neighborhood is the local bubble, a region of interstellar plasma spanning hundreds of light-years with a density much lower than the surrounding medium. The solar system has been traveling through this bubble for the last 5 to 10 million years. The cause of the local bubble is uncertain, but the leading theory is that a series of supernovae swept out a cavity in the surrounding plasma. Evidence of these supernovae has been found in the form of rare isotopes like iron-60 in the Earth's seabed and Antarctic ice. Throughout his 1,000-year journey, Battuta remained silent, monitoring changes in density and temperature and recording first-hand data as he crossed the Helios Heath and entered the local bubble. He felt the sting of cosmic rays and diligently repaired his scars. He remembered how Voyager 1 and his later siblings bravely sailed into the endless darkness. Behind him, the Sun grew smaller and dimmer until, to his instruments, it became just another ordinary star. 10,000 years later, Battuta plunged into the void, the abyss between stars. His true interstellar journey had finally begun. 100,000 years have passed since Battuta left Earth, and near the end of this leg of his journey, the probe decided to change course. His new target is 90 light-years from Earth. This change added 8,000 years to his total trajectory, but he deemed it worth the cost. This spacecraft loves human history, repeatedly studying the books, star maps, and digital archives uploaded to his system. He was deeply drawn to a single star, Algol, the demon star. 3,200 years ago, an ancient Egyptian calendar listed it as an unlucky star. In Greek mythology, it represents the severed head of Medusa, held by the hero Perseus. In Chinese astronomy, this star is known as a member of the Mausoleum constellation, specifically the fifth star. In modern science, it bears a more formal name, Beta Persei. In the 17th century, the Italian astronomer Montanari discovered that Algol's brightness flickered strangely. Over a century later, careful observers noted its periodic nature. Roughly every 2.9 days, the demon star abruptly dims for several hours before returning to its former brilliance. It wasn't until the 19th century that Edward Pickering of the Harvard Observatory revealed the truth. Algol's variation isn't the pulse of a single star, but the dance of two. A bright, hot primary star is orbited by a cooler companion. From our perspective, when the companion passes in front of the primary, the entire system appears to dim. While this seems straightforward, Algol's configuration reveals a violent history. Usually, more massive stars burn through their fuel faster and age more quickly. However, in this system, the more massive star is still in its youth, while the smaller one is nearing the end of its life as a subgiant. The solution to this paradox is mass transfer. When the smaller star expanded into a red giant, it overflowed its Roche lobe, allowing the primary star to vampirically siphon away its hydrogen. Algol is just one example of the multi-star systems common throughout our galaxy, ranging from simple binaries to complex arrangements of 9 stars, like the Alpha Centauri system, where Proxima Centauri orbits a central pair from a great distance. The best place to view these wonders of the galaxy is from the deck of a ship. On a clear night at sea, the stars fall like dust across the horizon. Imagine a young mind in the early 19th century, far from home and hungry for knowledge, being completely captivated by this sight. In 1784, Friedrich Bessel was born. He was not a typical astronomer. He dropped out of school at 14 because he hated Latin, using his mathematical talent in an import-export firm. His proximity to shipping ignited a curiosity about navigation, which led him to the stars. Soon, his talent was recognized after he successfully measured the orbit of a comet. He faced a choice between a comfortable career as a merchant or a position as an assistant in a private observatory. He chose the stars. His target was 61 Cygni, known as the flying star for its rapid movement. He correctly guessed that this high velocity suggested the star was nearby, and therefore its distance could be measured. When he finally calculated the distance, it was so vast that he had to invent a new unit. Miles, kilometers, and even astronomical units resulted in numbers too cumbersome to use. Thus, he created the light year, the distance light travels in 1 year. Using this term, he announced that 61 Cygni was roughly 10 light years away. Yet, it is neither the closest nor the most peculiar star. Take Betelgeuse, the 10th brightest star in the sky. Though it is 450 light years away, it is so massive, at least 15 times the mass of the Sun, that its diameter is more than 750 times larger than our own star. If placed at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and much of the asteroid belt. Betelgeuse is bloated and misshapen, no longer a perfect sphere. Imaging shows its surface is lumpy, roiling with internal instability. In late 2019, it unexpectedly dimmed, dropping out of the top 20 brightest stars. This was likely caused by a massive ejection of superheated plasma that cooled into a dust cloud, temporarily blocking its light. Once the dust cleared, Betelgeuse recovered, but it will not live much longer. Within the next 100,000 years, it will end its life in a supernova. Theoretical models suggest its peak brightness could rival a half-moon, outshining every other star and planet in the night sky. It will be a piercing point of light, bright enough to read by at midnight, before fading away within weeks, leaving the shoulder of Orion empty forever. However, most stars are not giants, they are medium-sized like our Sun or smaller red dwarfs, such as Proxima Centauri. Only visible through a telescope, Proxima Centauri is extraordinary because it hosts a small rocky planet, Proxima b, which is similar in size and mass to Earth and resides in its star's habitable zone. Thanks to projects like the pale red dot, we know this planet represents our closest opportunity for life beyond the solar system. There are no guarantees. We cannot yet confirm the presence of liquid water or a stable atmosphere. To remain habitable, a planet must orbit very close to a red dwarf. Proxima b orbits at only 0.05 astronomical units far closer than Mercury is to the Sun because red dwarfs are so dim. Yet life there would not be easy. Red dwarfs are temperamental, star spots can cover half their surface, and they are prone to violent electromagnetic storms. The planet's environment would alternate between extreme cold and intense radiation. Worse, Proxima b is likely tidally locked, with one side in eternal day and the other in eternal night. Even so, it is not necessarily a dead world. Simulations suggest that with enough water and atmosphere, heat could circulate globally, preventing the day side from scorching and the night side from freezing into an atmospheric collapse. The most intriguing possibility is a ribbon world, a narrow twilight zone between the two extremes where the temperature remains balanced enough for life to survive. Proxima b is just the beginning. The galaxy contains an endless variety of worlds. Conservative estimates suggest at least one planet for every star, meaning there are hundreds of billions, perhaps trillions, in the Milky Way alone. There must be twins of our solar system, as well as exotic systems like TRAPPIST-1, where 7 rocky planets huddle close to their star. There are hot Jupiters being slowly evaporated by their suns, super-Earths and mini-Neptunes shrouded in thick hydrogen mists, and worlds covered entirely by oceans or encased in ice. There are even rogue planets, belonging to no star system, drifting alone through the dark. Battuta could never visit them all, so after a brief 10,000-year detour to Algol, he returned to his primary course, heading toward the galactic center. He knew that for the first million years of this journey, there might not be much to learn, as this region showed no signs of life or exotic physics. To find the truly extraordinary, he would have to go deeper, into the heart of the Milky Way. An internal alarm reminded Battuta that it was his 1 millionth birthday since achieving consciousness. He was currently located in the Scutum Centaurus spiral arm, about 15,000 light-years from the galactic center. He paused near a protoplanetary disk, a swirling ring of dust in the earliest stages of planet formation. Although he intended to leave quickly, the birth of a planet was too significant to ignore. Even in the long history of humanity, no civilization lived long enough to witness the entire process from start to finish. So, Battuta decided to stay and observe. This story of planet formation is the story of life itself, beginning with the fundamental elements: hydrogen, carbon, oxygen, nitrogen, and phosphorus. Hydrogen was born in the fires of the Big Bang, forged within the first few minutes of the universe. The rest of the elements were forged in the hearts of stars, a concept proven by the landmark 1957 paper known as B²FH. Authored by Margaret and Jeffrey Burbidge, William Fowler, and Fred Hoyle. They proved that stars are not just lights in the sky, but forges for the elements of the periodic table. Every stellar death enriches the cosmos, adding heavy elements to the interstellar stream for the next generation of planets. The galaxy is dotted with thousands of nebulae, such as the Horsehead Nebula in Orion, a dense region of active star birth. In contrast, the Red Spider Nebula is a graveyard, where the remnants of a dying star are cast out into space. A planetary system begins with a vast molecular cloud. In the early 20th century, James Jeans described the mechanism of how these clouds collapse. Any disturbance, often caused by the cloud passing through a galactic spiral arm, can trigger a gravitational collapse. Most of the material gathers at the center to form a protostar, while the remaining matter flattens into a rotating disk. Inside the disk, dust particles collide and stick together. Near the young star, only heat-resistant materials like iron and silicates can survive, forming rocky worlds. Beyond the snow line, where temperatures are lower, ices can condense, leading to the formation of gas giants. The first large embryo to form wins the gravitational lottery, sweeping up most of the gas to become a giant planet. In our own solar system, the giant planets likely formed closer to the Sun before migrating outward. Some may have even been ejected from the system entirely. Having watched this small miracle unfold, Battuta prepared to continue his journey. This time, his goal was clear: the heart of the Milky Way, where he would face the supermassive black hole and the darkness beyond.